All right, good morning everyone, and welcome to DEV205. This is developing applications in AWS on the JVM, and we're going to focus most of today's session on the AWS SDK for Java. My name's Kyle Thompson. I'm a senior engineer on the AWS SDK and tools team, and I spend most of my time on the Java SDK. So before we start, can I get a show of hands for people who've used version 1 of the AWS SDK for Java? Okay, so we've got a few people out there. Okay, great. So as I say, we're going to spend most of the time talking about the SDK, but not version 1. We're going to do a little recap of version 1, take a look at where we are now and some of the high-level libraries that version 1 exposes. And then we're going to jump into version 2, which is currently in developer preview. So this is kind of our upcoming next version of the Java SDK. So again, can I get a show of hands for anyone who's looked at version 2 of the SDK? A couple of hands. Okay, good, good. I think this is going to be good then. So let's start off with a recap of the current version of the SDK. So this is the version that's in production today. It's open source, it's available on GitHub, and by way of a little bit of history, we released the first version of the AWS SDK for Java back in March 2010. At that time, it was a single Maven module. We supported 9 services, so we exposed the APIs of 9 services in Java bindings, and then over the years, we've kind of developed it, added new services, of course. In 2014, we separated out the single monolithic project into separate Maven modules, so we now have one Maven module per service API, all the way through to the present day, where now we support over 100 service APIs. So that's not necessarily 100 services. Some services expose more than one API for different parts of their surface area, and we support all of those. And we've added a number of high-level libraries that sit on top of those low-level SDKs over the years. So let's take a look at some of those. So in the middle here, we've got the AWS SDK for Java, which is my product, the thing that we vend out on GitHub. And then associated with it are a number of other high-level libraries. So these are the green boxes. They sit on top of those high-level libraries and give you kind of Java-specific enhancements to the low-level service APIs. So some interesting ones here, the DynamoDB Mapper, for example. We're going to go into some of these in a little bit more detail. We've got some DSLs for kind of building IAM policies and step functions. These are things that ship with the SDK. So when you pull in, for example, the S3 module, you'll get the S3 encryption client and the Transfer Manager client along with it. So these are available in our public GitHub repository, and they ship with the SDK. But outside of that, there's also a number of other AWS-owned but Java-focused libraries that we vend out. So these are also, most of them are available on GitHub, some of them in our AWS Labs organization, some in the core AWS organization. These are things like on the left-hand side here, the Kinesis producer and consumer libraries, allowing you to put high throughput into Kinesis. These sit on top of the Java SDK. Another interesting one is the AWS Scala SDK. I don't know if people have seen this one before, but this is kind of a code generation plugin for your Maven project that will generate Scala-ish bindings on top of the Java SDK. But they sit on top of and call down to the core Java SDK. So these are AWS-owned, AWS-managed open source products. Then the next kind of, I guess, suite of libraries are third-party ones. So these are open source. These are not AWS-managed, not AWS-owned, but they're libraries that third parties have built, again, on top of and using the AWS SDK for Java. So I guess the point I wanted to get across here is there is the core AWS SDK for Java, which mirrors the service APIs. And then you have this broader ecosystem of other client-side libraries. Now, everything in the north of this diagram is client-side. So these are built into your application, you'll either pull down a dependency, or it's going to kind of help you during development time in the case of the Eclipse toolkit, for example. But they're something that you would use as part of your application development. But then there's kind of another side to this, and that's how do you get your Java applications actually running in AWS? And we have a number of services in this domain as well. So on the left-hand side in that execution environments box, these are a number of ways that you can run a Java application within AWS. And many of them have Java-specific abilities. So for example, Elastic Beanstalk has got Java-specific bindings. AWS Lambda, of course, has Java runtime. And we're going to look at Elastic Beanstalk in the demo a little later on. But this is kind of a high-level view of the Java ecosystem within AWS. So I mentioned that I wanted to kind of do a little review of some of the high-level abstractions that we have produced in V1. So these were the green boxes on the previous slide. These are things that ship with the SDK that are available to you when you pull down the Maven dependency. So the first one is AWS Transfer Manager. Can I get a show of hands again? Who has seen or used Transfer Manager before? Okay, a few hands, half a dozen hands. So Transfer Manager is our kind of file and directory-based library that sits on top of Amazon S3. And it allows you to asynchronously copy objects into and out of Amazon S3 using the file system. Because we have knowledge of the file system and it's this stateful thing, it allows us to do more sophisticated exception and error handling that you wouldn't necessarily be able to do from a raw server-side API. So we can do things like better retries and exception handling. It also has support for multi-part upload, so you don't need to worry about splitting your large objects to be able to take advantage of that. The Transfer Manager can take care of that for you. And of course, there's hooks for progress reporting. Because this is an asynchronous API, you don't necessarily block when you call it. You need a way to kind of understand what's going on. And you'll see the second last line in that code snippet there has an add progress listener to our download object. So this is the way you'd kind of hook in a progress listener to an ongoing download. So that's AWS Transfer Manager. Really, all you need to do is give it an S3 client. So that's the low-level service API client, and you can start using it. Next up is the DynamoDB Mapper. So again, a show of hands for people who've used or heard of the DynamoDB Mapper before. Okay, a few more people. So this is our effectively ORM. It's an annotation-based object mapper from a Java POJO into a DynamoDB document. So you simply annotate the class that you want to serialize, and in this case, we're going to call the table people. So you give it a table name. This is the destination where your objects are going to go to. Then you need to tell it what property of your object is the key, and the rest it can infer through reflection. So it will automatically pull out the fact that there's a getAge property and set the appropriate DynamoDB data type. And then loading and saving is as simple as those three lines at the bottom. I can give it an annotated class and a key, and it will be able to load the object from the DynamoDB table. And then similarly, I can mutate that thing and save it back. That's DynamoDB Mapper. So the final one I want to look at is the DynamoDB Document API. Who's used this one? Wow, maybe 3 people. OK, excellent. Well, hopefully you'll learn something today. So the Document API is kind of a Java-friendly API that sits on top of the DynamoDB low-level client. And it means that you can work more natively with Java types. And there's a few kind of interesting properties about it. The first is that it's what I call a resource-based API. So rather than making operations on the top-level Dynamo client, like put item where you have to specify a table and a key in the item and all that sort of stuff, you can call getTable, which is the kind of middle line here, so DynamoDB Document API.getTable, and I give it the people table, and that's going to give me a table object. So that object represents the DynamoDB table and holds a link to the underlying DynamoDB client. And so I can just perform operations directly on that thing now. So I can do scans, I can do put item requests, I can get items, and it's kind of, you don't need to worry about plugging in the table name anymore. That's all encapsulated within that object. The second interesting property about it is that it handles pagination for you. So the very last line in this code snippet is a scan, and it's going to give me back an iterable, and it's going to take care of paging those items in the background. So there's no need for you to kind of figure out what the last evaluated key was and plug that into a subsequent request. The mapper's going to do that, or the document API is going to do that for you. So they're kind of the high-level APIs of version 1 that I wanted to talk about. And now we're going to dive into V2. So version 2 of the SDK is in developer preview. And what I mean by that is we don't recommend it for production use at the moment. AWS has a fairly strong stance when it comes to backwards compatibility. We don't like breaking customers. And so but at the same time, with the developer preview, we want the freedom to be able to change the API from feedback that we get through the developer preview process. And that's kind of where you guys come in. What we really, really need is as much feedback as possible on the developer preview in this forming stage, in this stage where we're free to, or relatively free to change the APIs in a potentially backwards incompatible way. Because once we release the GA of the V2, we're going to be kind of locked into those APIs for those reasons of backwards compatibility. So why now? Why V2 now? Why does it make sense to do it at this point? Well, I mentioned at the start that the first version of the SDK was released in 2010. So a lot's happened in the Java ecosystem since then. Our first version actually baselined on Java 9, and in September this year, in our first version baselined on Java 5, and in September this year, Java 9 was released. So there's kind of a big evolution that's happened in the Java ecosystem. And we've had feedback from customers that they want to be able to take advantage from that. We've also had a bunch of other feedback from customers over the years about either ways to change the API or behaviors that perhaps the V1 version of the SDK doesn't make sense, but we have to keep them for backwards compatibility reasons because other customers may be relying on those behaviors. And we've kind of hit this tipping point now where we've got enough feedback and there's been enough evolution that it makes sense for us to do a new version. So in June this year, we released a developer preview of V2, and we did so kind of under a set of core principles that we wanted to adopt and develop the product under. The first one was, we want this to be a community product. This is your SDK. We want you to use it, and we want you to help us drive its evolution. And so with that, we wanted to be very, very open. And as soon as we had a kind of minimally viable product, we open sourced it on GitHub, and we've been accepting kind of pull requests and feedback and conversations about the way the API looks ever since. And we really want that feedback. The second is we understood that it wouldn't necessarily be feasible for customers who had a large investment in existing applications using V1 of the SDK to be able to have to migrate big bang. You know, that's a big ask. And so we wanted customers to be able to run both versions side by side. And we've done that by separating them into different Maven package groups and the different Java packages as well. And actually, the demo that I'm going to be going over in just a little bit is a project that contains both versions of the SDK running side by side. So the next principle was making simple things simple and complex things possible. So what I mean by this is we wanted the kind of the coalface, the entry point to the SDK to be those use cases that you're going to do most often. You shouldn't have to kind of dig into the depths of the SDK to do something that's really common. But at the same time, you want to be able to have the flexibility to do complex things if you have different use cases. And so that's where this tenet of simple things simple and complex things possible comes in. And we use that to drive our design decisions. And then finally, like everything at AWS, we're constantly trying to improve the performance. And we've got a kind of a different take on that I'm going to take you over as well. So first up, let's start looking at some of the changes. So I mentioned that customers would need time to migrate, and that's because there have been a number of changes to the programming API that will affect how you use the SDK. So first up, immutability. In a concurrent multi-threaded world, immutability is king. It helps us with the ability to reason about our code if things aren't constantly changing underneath you. And in V1 of the SDK, all of the clients, so the things that expose the service operations, and the models, the things that you make your requests with, are fully mutable objects. And so for V2, we wanted to move away from that. In some of the new functional patterns that have come out in Java 8, immutability is kind of assumed, and so we really want to take full advantage of that. And so clients and models in V2 are immutable, and that's come with it some interesting properties that we're going to go into. The next three, enhanced pagination, smart configuration merging, and forward-compatible enums, these are things that, along with the tenet of making simple things simple. So the AWS services give us models that we use to generate these SDKs, and along with those models are metadata that we can tell when a service operation is paged, including what the tokens are and where they belong in subsequent requests. It makes sense for the SDK to expose that. It doesn't make sense for us to pass that pain on to customers. So that's enhanced pagination. Smart configuration merging, so for those of you who've used V1 of the SDK, you'll know that there is a kind of monolithic configuration object with hundreds of different options on it. We wanted that to be simpler. We've grouped like configuration options. We've stripped out a bunch that don't really make sense, and we've made it such that you can configure just pieces of the application and then still pull in the defaults that we recommend and just override the things that you want. And the third is forward-compatible enums. So again, this is making simple things simple. If a service API exposes a property like a status that has an enumeration, it makes sense for you to be able to access that thing first class. But in the current version of the SDK, you need to know that a property is an enumeration and then go find the appropriate enumeration for it and do the parsing yourself. One of the reasons for that is because we didn't have a way to expose those enums without locking service teams into that set. And service teams need to be able to add statuses over time. So forward-compatible enum solves that problem. And then finally, our streaming operations. So streaming operations within AWS are slightly different to your regular request response operations. So what I mean by a streaming operation is, for example, get object from S3, where you get a response back and then you get an input stream that has a stream of bytes that are coming down the wire. When the client returns you that response, S3 might still be sending data, and you need to be able to consume that in your client application. If you don't, then the connection's going to get caught in a funny state. That's going to cause contention in your connection pool and a host of problems. And at the moment in V2, streaming operations and non-streaming operations look the same. So there's really no indicator that these things are special and require special handling. So that's where the streaming operations come into place, and we're going to have a look at some examples of those. So let's dive in and have a look at immutability and what that means to the SDK. So this is a snippet of code from V1. This is how you would create a service client. So I'm going to new it up. It's for the simple email service. I'm going to tell it where I want to find my credentials. And then I want to operate in US West 2. So I immediately call setRegion on it. And this is like a really, really common pattern for creating a service client. But there's a problem with it. As soon as I call setRegion, what have I done? I've mutated it. So in a mutable world, we can't do that. Last year, we introduced with V1 of the SDK the builder pattern. So you could create clients that were kind of runtime immutable using a builder pattern. And in V2, we've kind of gone all in on that pattern. But it's not just runtime immutable, it's also compile time immutable. So this is the same code to create an SES client in version 2 of the SDK. Because Java 8 allows us to have static methods on interfaces, we don't even need to worry about the underlying implementation class anymore. All you need to worry about is the SES client is what I want. I do SES client.builder, I apply my configurations, and then I hit build, and I get an immutable instance of an SES client. So that's immutable clients. Immutable models, again, this is an example of how you would call the send email operation on SES. And you can see it's this large nested structure. You know, I need to set up a destination. I need to set up a body. I need to set up reply to addresses. There's this hierarchical structure that we're creating here. And we're using the with pattern. So I'm going to do a new send email request, and then I'm going to do with destination, with reply to address, with message. Kind of a fluid style there. And every one of those withers is mutating the original object. So of course, in immutable land, we can't do this. So how do we do that in V2? Well, we use builders, of course. But this is looking pretty big and pretty verbose. So you'll see here we've created a same pattern. So you know, the object that I'm after .builder, and then I apply my mutations, and then I call build, and I get the immutable representation of it. But it's kind of getting a little bit verbose. I've got this string of build statements at the end to build up this thing. And we thought, you know, there must be a better way. This is one way, and we've exposed this way, and you can absolutely use this if you prefer this verbose style. But there's also another option. We've added, for each one of these operations where you're setting a complex type that requires a builder, there'll be a method that looks something like this, which is a little bit confusing at first. It's a consumer of a send email request builder. Effectively what we're doing, or what the SDK is doing, is creating the builder on your behalf, and then you apply mutations to it, and then we'll build it for you. And what that means is you can do the same code above in these 5 lines. So here and I'm using Java 8 lambdas, of course, so I can do r-r.destination, and then I can set addresses. This is going to produce the same object as that big hierarchical structure. And people who are perhaps from a Scala background might understand this a little because it's a little bit similar to name parameters. It's kind of the best we can do within the Java ecosystem. So that's how we create immutable models. But let's say we've already got a request object, and the only thing we want to do is change where it's going to. We want to change where the email's going to. We need to set a new destination. In V2, this is how we do that. We would just call with destination on the original object and mutate it, and then pass it back into the client to make a subsequent request. Of course, you know, the pattern's getting old by now. That's not immutable, so we can't do that. In V2, what you would do is something like this. Every immutable object within V2 of the SDK has a toBuilder method on it. And that gets you back to a mutable representation of that thing using the state of the immutable instance. And then you apply whatever mutations you need and hit build. So hopefully pretty straightforward. But again, we wanted to make this less verbose. So this is certainly one option that's available to you. But there's also a copy method on our immutable objects, which again takes that consumer builder pattern. So using a lambda, you can apply whatever mutations you want. Under the hood, the copy will then call build for you, and it will give you back a new send email request. So I should point out that, of course, this is a new instance. We haven't mutated the original request. The original request has remained the same. So that's immutability and how it's affected our APIs. Next up is enhanced pagination. So who's used a paging operation within V1 of the SDK before? Okay, so you're kind of a little bit familiar with this pattern where you make a request, you get the result, you do what you needed with it. So in this case, I'm getting the table names and printing them out to stand it out. And then I need to check if this was the last page. And if it wasn't, I need to make a subsequent request, and I need to keep doing this in a loop until that last evaluated page name is null, and I get no other objects back. So as I said, we have some metadata about paged APIs, so it makes sense for us to expose something nicer. And in V2, we've exposed this iterable concept. So I should point out that iterable is kind of like we went back and forth in our team what to call this thing. So if you've got any great ideas about what to call it, then I'm all ears. But at the moment, it's called an iterable, and it mirrors the operation name. So in this case, a list tables iterable. And what this gives you back is an object of type SDK iterable, which extends a regular iterable. So you can get an iterator from it and put it into a regular for loop or a for each. And it also exposes a stream method that gives you a Java 8 style stream. But what are you iterating over, or what are you streaming over? In this case, you're streaming over the responses themselves. So you're streaming over the pages. So in this case, I'm going to flat map each page to pull out the table names, convert them to a stream, and print them out to stand it out. So this is in one line what I've done in 4 or 5 lines in V1 above. But again, we have about some paged APIs. Not only do we know the token and that it's paged and where the tokens belong, we know what it is that's being paged. So what property of the response is the thing that's a list? And in that case, we also expose on the response to that list table's iterable a method that mirrors the thing that's being iterated. So in this case, table names. So here, what we're going to get is an SDK iterable of table names, which in the case of DynamoDB is a string. And so I can just directly print them to stand it out. And we also get, so that was the iterator portion, we also get a stream on that thing as well, or get the ability to do a stream, so I can do complex things using the Java 8 streaming API, so filtering and all that sort of good stuff. So that's enhanced pagination in V2. Next up is the streaming API. So I wanted to talk a little bit about them because it's kind of a different pattern than V1. So this is a block of V1 code. This is the Amazon Poly service and the synthesized speech operation. So synthesized speech takes a string of text and it gives you back an audio representation of that in the form of a stream of bytes. So the result object that you get here, somewhere in it has an input stream that you need to read from. And if you know that, you've read the service API, then great. If you haven't, and you just assume that the result is like a normal response that's already been marshaled and all the stuff's been read from the wire, then you might forget to read that input stream. And so then your connection's going to get caught in a funny state. In V2, we wanted to expose this differently. So it's much, much more obvious that streaming APIs require special handling. And we've done that with 3 overloads. So the first looks very, very similar to the V1 one. You call the operation with a request, you get a response object, but it's actually a wrapper object. So the response itself is an input stream, and it's denoted by this response input stream object. And then within it is the actual type, the marshaled portion of the response. So you can pass this straight into a try with resources block and do what you need to do with it. The second option is with a callback. So you pass, along with your request to the operation, you pass a streaming response handler, and this is just a functional interface, so I can shorten this using lambdas to this. But the point is here, I get a response and I get an input stream, and it's very, very obvious to me that I need to do something with that input stream. So in this case, I'm copying it to a file. So you might have noticed a pattern where all 3 of these examples take that input stream and just write it to a file. And we found ourselves doing this a lot during development as well. So we thought, doesn't it just make sense for streaming operations that are dealing with bytes of data coming over the wire for us to just expose a file overload as well? So there's the third overload where I pass a request, I pass a destination file, which is a java.nio.path, and that we will take care of actually serializing it to disk on your behalf and making sure that the connection gets cleaned up. So they're the streaming APIs. Next up is pluggable HTTP. So this is the complex things possible portion of our simple complex things possible tenant. And we had a lot of requests from customers over the years to tweak the HTTP configuration in specific ways for their use cases. And because we were tightly coupled in V1, we're tightly coupled to the Apache client, we weren't able to do that. So with V2, we've split these things out. And now you can swap the HTTP client at runtime. And the other important aspect here, which is going to come into play in a couple of slides, is the fact that we have first-class support for synchronous and asynchronous clients all the way down the stack. They are different beasts, they look different, and they have different implementations. We're going to ship the SDK with a number of default implementations that are available to use, and each of them kind of has its own advantages. So that's pluggable HTTP. That's going to come into play in just a little bit. So performance. One of our biggest requests for V1 of the SDK was to have a non-blocking implementation of the HTTP layer. As it is today, V1 uses the Apache Commons HTTP client, which is a blocking HTTP client. It takes up a thread per request. We're going to look at a little bit why it does that. But with V2, we've got a neti-backed non-blocking IO implementation. Who here understands the kind of ins and outs of non-blocking IO? Okay, there's a few. So for those who don't, I want to do a little bit of a dive into what I mean by non-blocking IO. And let's have a look at what happens when you make a request to AWS using one of the synchronous clients. So I'm the caller, I've got an instance of an SDK client, I'm going to send in my request POJO. Then the SDK is going to serialize that to the wire format, so JSON or XML or whatever the service is expecting. We're going to make an HTTP request, we're going to stream bytes to the wire. We're going to then wait for a response and stream bytes back again. We're going to deserialize them to the Java representation that you're looking for the response and give that back to you. And in synchronous land, all of this happens in the caller's thread. So the caller can't do anything while this is going on. V1 of the SDK includes an asynchronous set of clients that you can use. And let's look at how that works. So again, you call it, you give it your POJO, and instead of waiting for that request to happen, we'll give you back a future immediately. And this is kind of a bucket, a promise to say we're going to put the result in here when we're done. But behind the scenes, what's happening is effectively the same thing. So bytes are being streamed out, bytes are being streamed in, deserialization's happening, and then the future completes. It's still, all that stuff is still happening in one thread. It's just happening in a thread pool that the SDK manages on your behalf. So let's look at what happens in the HTTP layer that means this is kind of necessary. So again, this is for our synchronous clients. Our Apache implementation might look something like this. We've got a connection pool. We're going to ask for a connection to an endpoint, DynamoDB, for example. It's going to, if it doesn't have a connection, it's going to go out onto the network and try and open a socket for that. And that's an IO operation, right? So that could be unbounded in terms of time. When that socket has been created and TLS negotiation has been done and all that good stuff, we get the socket and we synchronously return the connection to the HTTP layer. So that initial request connection call was a blocking call. And then once it's got that connection, it can stream bytes to it. And again, it's going to do this in a blocking way. It's going to put until it's kind of told that it can put some more and keep doing that in the thread. And then similarly, when the response comes back, it's going to ask the socket or ask the connection, do you have bytes for me? Wait and tell me when you've got bytes available. And I'm just going to wait here. So all of this happens in a single thread still. Even though in the V1 asynchronous implementations, the SDK is managing a thread pool for you, that's still happening in a single thread. So what's wrong with that? Each request then requires a thread. A thread is a piece of system resources. It uses resources like CPU. And those resources could be used for other things. And instead, they're just sitting there kind of waiting for the network to respond. That's stuff that the operating system can deal with. So that's where non-blocking IO comes in. So it introduces this concept of an event loop and an event-based way of communicating between layers. So the event loop is just a thread. There's nothing really special about it. It's just about how it interacts with the other pieces that make it different. So when the HTTP layer calls request connection, it passes along with it a callback to say, let me know here when that connection is available. And then it goes off and does something else. The event loop will take that request and asynchronously ask the operating system to open a socket. And once that socket's open, it's going to notify the caller that, hey, your socket's ready. You can put some data in it now. And so the HTTP layer, again, is going to, in a non-blocking fashion, call send bytes and tell me here when you're done. The event loop is similarly going to tell the socket, it's going to basically wait on the socket to be ready for write. But the difference here between this and, say, the synchronous Apache implementation is that it's going to ask the socket to tell it immediately if it's ready for write or not. And if the socket is not, it will move on and do something else, the event loop, that is. So we're going to do this a few times until we've sent our request. And then, again, the event loop is going to, when we're reading on the way back, the event loop is going to ask the socket, hey, do you have any data for me? And the socket's either going to say no, in which case the event loop's going to go away and do something else, or it's going to say, yes, here they are. It's not waiting for those bytes to be available. So again, those events are going to get streamed back to the client. So in terms of how these callbacks work, on the left side of the event loop, these are just application-level callbacks. So completable futures, or in the case of the Netty implementation, Netty has their own implementation of a future. And on the right-hand side, it's kind of OS-level polling in a non-blocking fashion. So the interesting property about this is because the event loop is not blocking when it's asking the socket for information, it actually has the ability to, with a single thread, manage multiple sockets at once. And that's really where the benefit of non-blocking IO comes in. You can, with a single application thread, manage multiple incoming sockets, or incoming outgoing sockets. So before we kind of go on, I wanted to just do a quick aside on how this has affected our threading model. So in V1 of the SDK, in both synchronous and asynchronous clients, our thread model looks like this. So the caller's thread in asynchronous land just kind of throws the POJO over the wire, and then it's done until that request completes. In Netty land, or in non-blocking land, we've modeled this slightly differently. So it might be a little hard to see the boxes up there, but the serialization to the wire format happens in the caller's thread in the case of our non-blocking IO implementation. And our reasoning for that is because you get the benefit of non-blocking IO when you start to go to the wire. Everything else is just CPU that's going to be used anyway. But this is our current thinking. As I mentioned a couple of times, we're in developer preview. This is open to change. So please, if you feel strongly about this, give us your feedback. Really, really want to hear from you. But this is kind of our current thinking. OK, so now we're going to drop in and see if we can actually look at the SDK in action. And hopefully my demo plays ball. It's been working all week, so we'll see how we go. So I've got a quote application. It's an application that's deployed to Elastic Beanstalk. It's backed by DynamoDB that's got a set of kind of famous quotes in it. And it's just a web application, very, very simple web application. And it is built in a Spring Boot application. And the crux of how we talk to DynamoDB is this interface here, so our quote provider interface, which, given an ID, will return a completable future for quote. So a promise that a quote's going to get put here once we hear back from DynamoDB. At the moment, we've only got one implementation of it, which is the V1 implementation. So this uses version 1 of the SDK's asynchronous client. So you can see here we've created the client. We're making a get quotes request. Because V1 of the SDK returns a future rather than a completable future, we need to do some work to kind of convert that thing to a completable future, and we do that using the futurity library. But what we want to do is we want to create a new version. We want to create a version that uses V2's non-blocking layer. So let's create that. We're going to create it in the same package, and we'll call it SDK V2. And we're going to implement that interface. OK, so first up, we're going to need a constructor because we need to create the DynamoDB client. And what do I need? So let's go back and have a look at V1. So V1, what do? We've got this configuration object. It's got max connections on it. It's got a no retry policy. It's got a region. OK, so these are things that we need to do in our implementation. Let's do the region first. So we can set this as a first class property. Region in our configuration is just a string, so we need to parse it. And we're going to need our configuration object. So let's get that into our constructor. Cool. So what else? We had max connections. Now this is where things start to get a little bit interesting in pluggable HTTP land. That max connections is a configured property of the HTTP client. And in pluggable land, we don't necessarily know what options an HTTP implementation is going to offer. And so by default, you need to then, as soon as you want to kind of drop into configuring your HTTP client, you need to provide a configuration specific to it. So again, I'm using this consumer builder pattern here in a Lambda. I'm going to provide it with a HTTP client factory, which we're going to create. So we're going to use the Netty version. So this is the Netty SDK HTTP client factory. And again, we're back to this builder pattern, so we can do things on this. So this is how we configure the Netty specific options of our HTTP layer, including a max connections per endpoint. So we can use our configuration max connections. OK, so there we go. What else did we need? Retries. So because we're going to do a little bit of a performance test later on, we don't want retries to come into play here. So I'm going to turn those off. And I'm going to do that by providing override configuration. So again, I'm using this builder pattern. And I can supply a retry policy. In this case, don't retry. Retry none. OK. So we want to make sure that we don't have the client is not a field at the moment, so we need to do that. All right, so now just a couple of pieces of housekeeping here. We want to make sure that we clean up after ourselves and clean up any resources that are in use. So we're going to close that client. And here's the kind of the crux of it. How do we actually get these objects from Dynamo? So I've got my client, and I'm going to call getItem. Kind of makes sense, right? And I'm going to use, again, this consumer builder pattern to construct my request. So this R object here is a getItem request builder. And on that, I have a number of properties that I need to set. Obviously, I need to set the table name. I need to set the key that I'm getting, which in our case is a ID, and it's the ID that's passed into the method. Now, this item builder thing here is a way to easily create a map of string to attribute value. In V2, we haven't implemented any of the higher level APIs that V1 exposes, and so this isn't a fully fledged DynamoDB Document API. It's just a little helper that means that you can create a map without having to kind of declare a mutable object and add things to it. And consistent read, I want to turn consistent read off because my quotes are just kind of static, so I don't need to worry too much about read consistency. Okay, I was going to return that. We know getItem on our asynchronous interfaces returns a completable future, but the IDE is complaining. So why is it complaining? Okay, it's the wrong type. So what getItem gives us back is a getItem response. What we want is a quote. So we need to kind of like map that thing. And thankfully, completable future gives us this option. So we have then apply, which is effectively a map method. And we're going to get this response. And this is only going to get invoked when the response has come back from the client, or come back from the service. And I want to create a quote here. And I've created a little static method to create one. OK, so it's happy. There's one final thing we need to do, and that is we need to tell our Spring application how to find this thing. So I'm going to do that by annotating it and giving it a name. Our V1 implementation we called V1, so I think it probably makes sense for us to call the V2 implementation V2. OK, so let's run this thing. So we're going to run the application. As I say, it's a Spring Boot application. We're just running this locally for the moment. And we're going to see if we can actually get make use of that. So we're going to go localhost first. And I'm going to give it provider. We'll look at the V1 one first. So this should hit the V1 provider. And we'll check if our V2 provider is working. OK, V2 is working. Great. Now, that's not much good to us because it's on my local machine. You know, my customers who are out there hungry for quotes about software are not going to be able to take advantage of this. So we want to deploy it to our Elastic Beanstalk instance. Let me check if it's there. No bean named V2. So I don't have that. I haven't deployed that bean yet. So I haven't deployed that change yet. So let's deploy it. And what I've done here is this project is a Maven project, and I'm using the third-party Beanstalker Maven plugin, which allows you to deploy applications to Beanstalk. So all I need to do here is I want to do a Maven clean deploy. And what that's going to do is it's going to package up using Spring Boot's kind of packaging framework. Then it's going to zip that thing up into a collection of all the classes. And it's going to upload that to S3. And then it's going to tell Beanstalk where to find it. So I'm going to kind of SSH into the instance. This was the thread dump from my can't find V2 provider. And this is Beanstalk has now picked up the fact there's a new version of the software. So it's rebooting the application now. And hopefully that shouldn't take too long. OK, great. So now what we should be able to do is hit this with V2. And there we go. So we've got an implementation of the non-blocking DynamoDB client deployed in Elastic Beanstalk using the Maven plugin. So that's kind of how we do the deployment. But what we want to understand a little bit about is kind of the performance characteristics of these two implementations. So version 1 uses a blocking HTTP client. We use a single thread per request. And so let's have a look at kind of a little perf run for that. So the application that I built also, as well as the web app portion to it, includes this perf tool with it, which is a very, very simple tool that will just hit the provider implementation that we give it with as many requests as it can handle, and we're going to see how many transactions per second we can get through in 30 seconds. So this is the SDK V1 provider. This is the original version 1 using asynchronous blocking implementation. So we're going to let this run for 30 seconds, and we're going to hope that doing a live demo here that this is going to give me the information that I'm hoping to give to you guys, but we'll see how we go. So we got through 99,000 requests. Our peak TPS was 5,100. And the interesting thing here, or maybe it's not interesting, maybe it's obvious, we used 109 threads. So we had 100 max connections, and as we know, every connection, every request uses a thread. So it kind of makes sense that we're going to have 109 connections. But let's switch to our V2 provider. So again, max connections 100. We're going to try and have 100 sockets open at once. And let's see how this thing performs. So at the moment, we've got 13 threads active in that JVM. So almost 10% fewer threads. Let's see how this goes. We've got to wait with bated breath, and hopefully it's going to perform similarly to the async implementation, the blocking implementation. We're using fewer threads, so it may not, but let's see how it goes. Okay, so what did we get in version 1? We got 99,000 total requests, so that's this number here, and a peak TPS of 5,100. With our non-blocking implementation, in the same amount of time, we got 125,000 requests with a peak of 5,200. So not that much bigger in terms of the TPS, but we got through more requests. But we used fewer threads. We used 10% as many threads. So that's kind of the power of non-blocking implementations. And you can, depending on the application type, it may make sense to use a blocking or a non-blocking implementation. It really depends on the use case and what are the constraints, the resource constraints on your application. So that's kind of a whirlwind tour of the AWS SDK for Java and some of the broader ecosystem, including how to deploy your code and how to get it running, of both V1, so hopefully you learned something about the high-level libraries that we expose, and V2 and the stuff that's coming down the pipe and that we're looking to release next year. So this is where you come in. We need you. We need your feedback. We need to know if we're going down the right track, because we really want V2 of the SDK to be your SDK, to be the SDK that you want to use. And so we have a number of mechanisms for you to give us feedback. As I say, we're in this awesome period right now where we can change things if we get feedback. Once we go GA next year, it's going to be a lot harder for us to change in terms of adapting to feedback and adapting to new feature requests if that involves backwards incompatible changes to our API. So here's a number of ways you can get in contact with us. You can prioritize the open features that we have on GitHub for V2 and kind of tell us what features you're really after. Follow our blog. You can email us directly. We're usually pretty good at getting back. We're active on Gitter. And of course, you can reach out to the wider community on Stack Overflow. So thank you very much.